Hello everybody. We're going to work on our last skill today with radical operations. At this point we've covered multiplying, we've covered addition and subtraction, we've covered simplifying square root expressions, we've even squared some, and we've used a distributive property. The last tool in our belt is how to work with dividing radicals, which is not that far different than the rules with multiplying, except the one nuance is why are we even worried about it? If, for instance, something like number 8 here on your screen has a completely simplified radical in the denominator. Well, that's part of dividing radicals, is the representation that's going to be accepted. That in mathematics, all the way up to your calculus classes in the future, radicals need to be left in the numerator. That's the first reason why we're going to go through this practice and just tell you that 2 over root 10 is not okay, because we don't want to have radicals in the denominator. The second reason why it's generally accepted is because remember that root 10 is an irrational number. It's a decimal, if you put it on your calculator, that does not repeat, cannot be written as a fraction. So it's a little awkward to divide 2 by a number that we can't quite put our finger on. So for that reason, to leave our answers in exact form, what we're going to do is we're going to run through a process called rationalizing denominators. We're going to do exactly what the process tells us to do. We're going to take the denominator you say for all 3 of these, and we are going to make the denominators rational numbers so we don't have to worry about dividing by that moving target. Now, to complete this process, what we're going to think about first is what would we be able to multiply root 20 by such that the product, what we get, would be a rational number? Well, the quickest way to do it would be to think about what we would do if we were able to multiply root 20 by itself. We've done this a lot in the past when we were simplifying. If you multiply root 20 by itself, you actually end up getting root 20 squared, which we of course know is just 20, because the square root and the square are inverse operations. But the big issue then is, well, hold on a second. When we're rationalizing denominators or dividing radicals, we're simplifying an expression that starts with a value. We can't multiply the bottom by root 20 because we're changing the value of the expression. So what we have to think about now is what are we allowed to multiply this expression by such that the value won't change, but we can re-represent it so that there's no irrational number in the denominator. Well, when it comes to mathematics, the one number you can multiply everything by to not change its value is 1. So what we want to do here is we want to come up with a form of 1 that takes care of 2 things for us. It takes care of this radical in the denominator, and it ensures that we're not changing the value of the initial expression. So our form of 1, based on what I wrote above in notes, definitely wants to get a radical 20 in the bottom here. This way we know when we get to the end there, we're just going to have 20 in our denominator, which is a rational number. How can we write a fraction that is equal to 1 with a root 20 in the bottom? Well, remember, anything divided by itself is the value of 1, so we can just use this form of 1, root 20 over root 20. Let's put a highlighter over that, because that's the main step here when it comes to rationalizing. We're generally looking to multiply by a form of 1 that's going to guarantee that the resulting denominator is going to be a rational number. Now, in this case, it doesn't have to be root 20. Another version that would work, that I'm not going to do on this video, but just to show you, you could have done root 5 over root 5, because root 5 times root 20 is root 100, which is 10. That's going to help us simplify less. But for the purpose of this video, we're going to just treat root 20 and root 20 as our way to do this. So again, now we're just going to multiply across with fractions. We're going to do negative 3 root 20. Negative 3 times root 20 is just negative 3 root 20. Root 20 times itself is the square root of 20 squared, which is just 20. Now, like all of our other radical expressions, we want to make sure our answers are completely simplified, which means 2 things. Make sure that the radical is completely simplified, that results, and make sure that the fraction that results is completely simplified. This is also why, by the way, going backwards, having this instead would have been helpful, because it's going to evade some of this issue with simplifying. You want to simplify the radical first, because you might be pulling some factors out and then have to simplify a fraction. There's no point in simplifying a fraction first, then the radical, then simplifying the fraction again. In this case, root 20 reduces to 2 root 5, because that's root 4 root 5. And that's going to all be over 20 still. And then that's going to give us a solution here. I could certainly multiply this and get negative 6 root 5. But I also could note that 2 over 20 reduces to 1 over 10. So really, if we run this product down, this is negative 3 times root 5, which is negative 3 root 5, all over 10. Our radical is completely simplified. Our fraction cannot be simplified any further because 3 and 10 do not share any factors other than 1. And we do not have a radical in the denominator anymore. So this is going to work out perfectly for our first rationalizing example. We have taken this opening denominator, these two expressions, negative 3 root 20, over root 20 rather, and negative 3 root 5 over 10 have the exact same value. It's just that now we have an expression that doesn't have a radical in the denominator, or an irrational number in the denominator. We've rationalized it. With 2 over root 10, this is a little bit more straightforward. We're going to want to multiply top and bottom by root 10. Now let's get to this last one. I'm going to handle this in 2 ways. So I'm certainly going to approach this like we just did, with one manner. But then I want to talk about a little sneaky shortcut type of deal that's going to help you with some efficiency, especially with your homework assignment. So let's start this, though, by completing it the first way. Clearly, if you want to rationalize here, we're going to multiply top and bottom by root 6. In doing so, we end up getting negative 4 root 18 over 6. Again, so now we have a lot to simplify here, which is why the efficient shortcut's going to help us. I'm going to do the root first, though, because I can cancel common factors then. We get negative 4 times root 18 reduces to 3 root 2, and that's all over 6. And then here you could cancel the 3 over 6 to make it 1 over 2, or you could just realize real quick that negative 4 times 3, root 2, is negative 12 root 2. Divide that by 6 and you get negative 2 root 2. So that's our final answer here, which is like starkly different. Take a look. These two values are the same. Negative 2 root 2 and negative 4 root 3 over root 6 is the same value, number-wise, mathematically. However, look at the difference in the way they're represented. This is clearly a number easier to work with as well, especially if you're looking for combination or adding and subtracting. Now, what I want to do, though, is just kind of talk about how we can make our lives a little bit easier here with a different path. So I'm going to draw this one here. I notice here, now this is where multiplication comes in. Remember, the rules of multiplication are that if you have two radicals and you multiply them together, they fall under the same radical. Well, the same thing happens with division. But also, just a property we're accustomed to with fractions is that if you have a common factor in the numerator and denominator, you're allowed to divide those to 1 to simplify your work. In other words, negative 4 root 3 and root 6, both these two, the numerator and denominator, have a common factor of root 3 because negative 4 root 3, this root 6 can be rewritten as root 2 times root 3. If you're allowed to multiply radicals together, you certainly can break them in factors. And by looking at this now, the fact that the root 3 are on top and bottom, we often use quote-unquote canceling, but it's really not canceling. It's really taking things that divide to 1 and just kind of getting that value out because anything times 1 is itself. This makes this fraction way easier to work with versus what we did here, right? There's going to be way less simplification here because we're getting the number smaller right away. We're pulling this factor out. So what we end up getting here is negative 4 over root 2, which then needs to be rationalized by just multiplying top and bottom by root 2. You could already see that the radical on top isn't going to have to be simplified because 2 is prime over 2, and then of course this fraction just divides to the answer we got. So a more efficient way to work, not necessary, but certainly helps you down the line, especially, remember, all of these numbers are pretty small. We'll be working with radicals that are far larger, so if you see this kind of common factor, whether the bigger number's up top or bottom, it doesn't matter. If you see common factors when you're trying to simplify, get those common factors out by dividing them to 1 so that your actual rationalization works a little bit easier. Okay, so summing up, this video covered how to make denominators rational numbers by rationalizing denominators. This is the process of dividing radicals, which is just another way of simplifying. We're not changing the value of any of these. We're just re-representing them without irrational numbers in the denominator. To do that, we're looking to multiply the top and bottom by a form of 1 that helps us get rid of the radical in the bottom. Now, the easy way to do it is just to match that number, because you know that number squared is going to square root is going to give you the value. But sometimes, like in this example here, picking another number strategically will avoid simplification later. Like having root 20 times root 5 here to get root 100 would have gotten us that 10 right away, would have made our lives a lot easier. Again, the last piece was if you can Simplify ahead of time by finding common factors in this path. A lot less work to do than here. And just imagine how much less work that'll be when these numbers get larger. All right, thanks for watching. I hope this helps. Let me know if you have any questions. Take care.